Okay, so Gibbs sampling was using the same motif statistical model, but it's the way it does the update is not deterministic, it's stochastic. And it was published by Chip Lawrence and Jun Liu. Jun Liu is my PhD advisor back in 1994. It's I think a way where statistics was best used in a biological problem. Another good use is another example is a false discovery rate. I think is the best example of statistics used in a good biological problem. Anyway, so the way it updates to do this iterative update is more stochastic, and it's more kind of a I'll show you how this works. So supposedly you have a whole bunch of input sequences. You can also randomly start a matrix. And to do that, what we can do is we just randomly pick some k-mers in each sequence. And we try to align them to, supposedly this is where the correct motif happens. But if we don't know where it is, we just, randomly pick a location, doesn't matter. And you put them together, you count the percentage of ACGTs, you make the matrix. And so, by the way, this is also done with NEM or the EM approach, but I just want to show you in here. Remember, in a probability matrix, we never want to have zeros. And so you have some pseudo count, a tiny little number, right? You give it to a little bit of pseudo count for A, a pseudo count for C, some pseudo count for G, and pseudo count for T. And this is the same you use throughout the whole process. You always give it a little pseudo count just so that your matrix never have zeros, okay? And so you just count how many number of times A is in the first position divided by all the sequences in there together. So you calculate this matrix. And so then you take out one sequence. And once this sequence is out, the matrix is slightly changed, right? Because the one sequence, you basically use the remaining one to construct the matrix. And then you use the existing matrix to score every atmer, in this case, so supposedly this is an atmer, in the input sequence. And it will give you a score, which is a likelihood ratio, the same as before, right? You have a matrix, you calculate what's the probability this atmer is coming from this matrix, divided by the probability this atmer is coming from the genome background. And so every atmer will be scored using this approach. You will get a number, right? And so I want to kind of show you, for example, if you have a input sequence like this, okay? And your motif matrix is like this. And you can see this current motif is not very strong. We are not seeing, 90% of something. It's like, 40%, slightly stronger than other bases. And this base is 50% T, but then the other bases are also pretty strong as well. So this is, in the sequence logo, you will see that the letters are pretty low. You don't have very strong dominant bases yet. Because we're still at the beginning of this algorithm, the motif is not going at, very strong trend yet. But if you just look at, this input sequence, maybe it's not very clear. You can see these are bold. A, T, C, A, G is, like I'm scoring this 5mer, then move one, and I keep moving. And then once I move into the right position, you can see here it's A, T, A, G. Let's see, sorry, A, T, sorry, the first position is A, T, C, A, G, right? So this is kind of the consensus sequence of the current motif. If you have that, you calculate this probability. So at every position, we calculate the likelihood ratio. At this base, it's slightly better than the background. Next base is slightly better than the background. And this base is slightly better than the background. And when you multiply these numbers together, you actually get a really high number. Whereas even a single base away, you can see, you scan the previous 5mer, that's kind of overlapping, right? So and every base you can see here, the numbers don't seem to matter to differ by that much, but when you multiply those together, wow, that's a tiny number, right? So whether you align well or not align well, the score can differ quite a bit, right? And that's why when you use the current motif matrix, even if it's weak, when you score all the k-mers in your input in one of your sequence that's taken out, you will get wildly fluctuating scores. And at the end, we do a sampling, which is we randomly do a draw, and the probability of picking a location is proportional to the totals, to the score in that position. And then you put this sequence back. And so supposedly in this case, we pick back the position 10. It's not the highest, but it's, you know, among the pretty high ones. There's no guarantee that I'll pick number 6. It's just by the draw, right? And then my motif is now slightly changed. I will take another sequence out. Oh, actually, I want to show you. So for hill climbing versus sampling, you know, hill climbing is you pick the best position, but that's more deterministic. In our case, we want to just kind of do a random sampling just so that we don't always guarantee that you will go to the local maximum. And so I want to show you like how you implement this sampling approach. Supposedly at every position, you get a score. This is also just a toy example. You have some score, and at each location, you also calculate a subtotal. So originally 3, plus 1 now is 4, plus 12 now is 16, plus 5 is 21, and plus 8 is 29, and so on. And in order to do a sampling, you do a random number of your final total. If the final total is 47, you actually put in your number in there, and it will create a new number. And then you find in this subtotal column, the first position that is the subtotal is larger than this random number you draw. And that will give you a sampling result. So I'll show you an example. So you can see here, at this point, you know, different positions, the score doesn't matter as much, and you just randomly draw, and you know, probably you'll have a higher chance of landing in here. But if you have a case like this, where the other scores are really low, and suddenly you have one sequence that matches motif really well, and usually this is because the motif is already taking shape when the matrix is like 0.89 or 0.95, you know, like pretty high scores. And so you can imagine when you calculate the subtotal is like this, right? And so if you were to do a random number generator and it give you 100, you will pick this location. If you do a random number generator, if you 200, you will go to this position. 300 will go to here, 400 will go to here, 500 will go to here, right? So many, many times when you do the random number generator, you will land in position 7. That's how you can see you have a better chance to go pick that position, proportional to their scores. Does that make sense? That's how you do sampling. And so with Gibbs sampler, then we put, you know, we take out the first sequence, we checked all the, you know, all the k-mers on this sequence. We find some, you know, some random draw proportional to the score, and we put the sequence back. The next thing is we take the second sequence out, and then the motif is slightly changed again because there's one guy that's gone. You use the existing matrix to score everybody again, and then you put them back again with sampling, and you iterate. You do, you know, first sequence, second. Basically, you do this over and over and over again, and magically, you will end up with an interesting motif. So, question about the process. Yes.
So this is if you don't know what motif you want?
You don't know the motif. It's completely random, and magically, it will converge on a motif. Another question?
Slightly confused. The sequences that you take at different locations or times, are those random across the genome, or are they in a particular region?
Okay. So the question is, how do you decide the pi, right? Initially, you don't care. You just randomly pick some locations in each sequence to initialize your pi. But later on, with every pi you select, this new path that you selected is based on, you do a random draw based on the position, the score at each position. And so this position that have high scores will have a better chance to be selected. But once you make a selection, that's the guy you pick. And then you'll put that sequence into the alignments now. Okay, next time you take out the second sequence, sorry, you take out the second sequence, you score all the input sequence, all the positions on this with the matrix, and then you do another random draw proportional to that score, and then you put the sequence back. And then you pick the third sequence, score all the aimers, sample to pick a location, put that sequence back, and so on. So magically, it will give you a motif. So let me ask you, if you start from the initial, like the same hill climbing example before that we see in expectation maximization, would we always end up in the same place in here? Is it deterministic? So Gibbs sampler is not a deterministic method, because remember that every time you do a sampling, that creates a little uncertainty. I would imagine when you are already in here, almost at the top of the mountain, you will probably go to the top. But when you are kind of low, you can still jump over the valley a little bit. So there's no guarantee that you always end the same. You probably still want to restart a number of times just to make sure that you will get a few different motifs. But there is no, so it's not as deterministic as EM approach. Okay. Other questions about Gibbs sampler? I will show you the intuition in a second.